Okay, so we'll go to the go to the practical where we can determine the velocity of sound using a set of tuning forks and end correction as well, right? Let's see. Earlier we did it with one tuning fork and using several harmonics. So we don't need to worry that much now because here we have like we always take the fundamental note in this one. So fundamental tone. So let's say there's a frequency tuning fork of frequency F. Okay. So we can say lambda by 4 is equal to L. Lambda is equal to 4L. Okay. V is equal to F lambda. F is equal to V over. Oh, I forgot the E again, right? There should be E here. L plus E. So lambda is equal to 4 times L plus E. So here we get uh, like V is equal to F into 4 times L plus E. Okay. V over 4F is equal to L plus E. And we get L is equal to V over 4 times 1 over F minus E. So this is also very simple. So this is Y is equal to, this is the independent variable. X is the dependent variable plus C. Okay. So if you plot a graph like this will be, this Y-intercept will be the end correction. Okay. And the gradient, you can say the gradient will be equal to V over 4. Therefore, the speed of sound means 4 times the gradient. All right. It is very simple. Okay. Here in the x-axis, you can't take the frequency straight away. You should take 1 over f, which is in hertz minus 1. And here you can take the length, which is in meters. Okay. This is the theory behind this practical. What you do is you take a certain fixed tuning fork of a certain fixed frequency, and then what you do is you vibrate it. Okay. You're going to calculate the resonance. Okay. You're going to calculate the resonance by taking the tube up and down, and at one moment when the frequency produced by this sound particles equal to the frequency of the tuning fork, it will show resonance and you will hear a larger sound. At that moment, you stop it. Okay. And then you take another frequency and then use another tuning fork of a different frequency and then do the same thing, get the length. Likewise, you can plot a graph. Okay. And using this graph, you can complete your practical. Okay. So let's look at the discussion. Here they are asking like, from what frequency do we start? Surely we should start with the highest frequency. Because the thing is now here we are considering fundamental overtones or simply the first harmonics. Okay. So the first harmonics have the least length. First harmonics have the least length. So normally when you do this practical, we should make sure that we will not miss the what? We will not miss the fundamental overtone. It's like this now. Let's say like when you do the practical, you just do the practical. Okay. You randomly hear a certain resonance. You randomly detect a certain resonance. But who knows whether this resonance is that of the fundamental overtone or that of the first overtone? We don't know, right? We don't know that exact. So due to that reason, it is advised to start at which point? We should start with the highest frequency. Okay. So if we start with the highest frequency, we can if we start at the highest frequency, we can make sure the length is small and we have not missed the uh, fundamental overtone. Okay. Right. From what frequency do we start to do this practical highest frequency and saturation? And to ensure the fundamental mode is taken in increasing resonance length or successively decreasing frequencies. Okay. So if you take 512 Hz, we should make sure that fundamental mode for 512 should be taken. Okay. Likewise. Why is it more easy to have here resonance of fundamental load? Now this is a very famous question, right? We did this in the sonometer question as well. Okay. If you take the fundamental overtone, the energy produced in the resonance of the fundamental overtone is very much higher than that of higher overtones. Use of immersion tube in water. Make closed end and get a variable length. Now these things are questions like, it's like this. Let's say you don't know the answer for this question and you are asked in the practical, why do we immerse the tube in water? You will sometimes get confused. You might have a lot of answers in your head. You might think, why are they asking this much easy questions? We are just doing that, right? But the thing is, like, you should know the answer to up to the exact points. Okay, so remember that, right? And then why is end correction introduced only in open end of the tube? In the, yeah, that's true. Like If it is like this, if it is an open tube, totally open tube like this, there are two end corrections. Okay. End correction is introduced in the open end because like whether we take the length, it's like this. We take the length L as this. But actually, I mean, at this point, we can show it ends at this surface X. But here, sometimes there can be a little bit deviation. This open ends. Okay, open ends can have deviations. Therefore, we put the end correction. Okay, uh, closed end will be an antinode and particle boundary. Yeah, the closed end is an antinode. Right? It doesn't have a displacement, so don't need to worry about that. But we should worry about this open ends. If alcohol is used, will L change? Okay, will the length change if alcohol is used? Like it's like this. If we use water and if you use a tuning fork of 100 hertz, let's say you got 10 centimeters. The question they're asking is, instead of water, if we use alcohol, will this length change? That's the question that they're asking. Okay. Obviously, it will change. Okay. Obviously, it will change. The reason is, uh, you know that the speed of sound in air, okay, depends on what average molecular mass of the air particles. Okay, we know that speed of sound in air depends on molecular mass of air particles. So if we use alcohol, this chemical composition can change. Therefore, the speed of sound in air will change. Let's look at the equation. See, according to this equation, L is equal to V over 4 times 1 over F minus E. Even if you use the same frequency, even if the end correction is same, okay, if we use alcohol instead of water, this thing will change. This velocity or speed of sound in air will change due to the vapor mixture, okay, which mixes with air particles and because of it created a different composition. So this length will change, okay, right. So that is the practical related to determining the velocity of sound and end correction using a set of tuning forks. Now, this practical is much more effective than the earlier one. In the earlier one, you should drag the tube very much higher and you should listen for resonances at very high overtones, third overtone, fourth overtone. That is not practical, okay? But in this one, there is no such difficulty. You have to increase the length of the tube, but like it's not increasing that much rapidly. Like you are doing it for several frequencies, right? It will have closer ranges. So that's it related to this practical. Okay.